So we've got three of them that are due, 271, 2, and 3. These are the copies of the problems that are out of the fall 2019 B or winter 2020 book. So does everybody have a copy of these? Because if you have the older book, you won't have a copy of these.
Can I get this? No, it's okay. Okay, I'll just drop it.
So we good? All right. All right, so these are kind of important here. We're kind of combining the use of equilibrium and coming up with a good strategy for that, and then doing some trigonometry too on these. So we've got the three of them. They're all similar in the basic outline of the approach to them. And you know, these are kind of important that you get the hang of these and can work through these. So let's have a look here. All right, so when you have this type of problem, here's my thinking on this. You know, what I'm going to do if working through this, or what I would suggest doing, is to start by making a simple free body diagram. And of course, that's how you pretty much start all of these. So what we're going to have on this one is I see a pin joint there. So I'm going to create RAY and RAX. I'm going to start with that. And then there's a cable over here. Now cables pull. Now you've given the angle, so that's going to be 51 degrees there. And then of course we have the couple. So that's what we're dealing with. Something like that. So we're good with that? And you know, I know that the free body diagrams can be a little tricky sometimes, but the thing I want to emphasize on this is don't overcomplicate it. I see a pin joint, I get two forces on there. That's all the thinking I do on that. I see a cable, I know a cable pulls at the angle of the cable. I don't overthink it. I don't do any more thinking than that. Okay. So that's step one. Yeah.
Is it always away from the pin joint?
The forces?
Yeah.
It doesn't really matter. It's just more how you draw them. I mean, so the question is, are the forces always away from the pin joint? The couple parts to that, there's kind of a two-part answer. The first part is it's just a matter of how I'm drawing it. I mean, the arrow is what matters. So if I'm drawing this, that would be the exact same effect as doing that, if you know what I mean. I mean, they're no different. The other thing is, if when I do that, I'm just assuming. I might be wrong in my assumption. And actually on that one, I think I am. I think that cable's going to pull it to the right. And so the actual reaction will be to the left. So you could assume right as I'm drawing there, or you could assume left, either one. You know, as long as it's a horizontal force for RAX, it doesn't matter how which one you assume. Is that answering your question or no?
Yeah.
Okay. All right. And of course, there's also an RAY on this too. All right. So either one of these would be fine. You could draw it up either way. It doesn't really make any difference. What all that matters is the direction of the arrow points. If you drew it to the left, that would be fine too. It doesn't make any difference. It all comes out in the wash on the answer. And actually, like I say, looking at that one, it could very well be that the reaction will be to the left. Okay. All right. Other questions on that? All right. We good? All right. Now the next thing I want to do is I want to do some trigonometry. Okay. So I have those reactions on there as I have them drawn. Now what's going to happen when I have this thing drawn up is I'm going to say to myself, okay, I've got three unknowns, which that's all you can handle with two-dimensional statics. And so I need to find a place where I can eliminate two of those unknowns from an equation and solve for the third. That's my thinking on this. And the place where that will occur is right up here at A. Because if I take a moment about A, RAX and RAY go right through A, so they don't cause any moment about A. If I take a moment about A, the only force I'll have to deal with is RC, and I can solve for it. So after I draw that free body diagram, I analyze the situation a bit, and I say, okay, I'm going to start this by taking a moment about A. And once I make that decision, what I want to do now is get X and Y dimensions from A to where the forces are, because that will make it easier to do the moments. Now, from A to B is pretty simple because it's vertical at 0.4 meters. But then I've got that angled bit of the bracket that goes from B to C. Okay. And so what I would want to do is to do the trigonometry on that. I'll have to figure out the angle. Okay, so I'll figure out that angle and then use from B to C as a hypotenuse of a right triangle and break it up into X and Y components using trig. Okay. So what I've got going on there is I've got 106 degrees. That's going to mean this is 26. So if I take 106 minus the right angle up above, which is 90, I'm going to get, that's, hang on now, that's 106, that's 16, right? Do I have a bust on that? Goodness gracious. I thought, oh boy, okay. That's a bit of a bust, okay, so I better have a look at that. Now I'm pretty sure this is cleaned up on the answers, though I'm not sure. So we better run through this one, okay? I think I've got an error on here. So let's have a look. All right, so we've got, that's not 26 as I'm showing us, 16. So let's see what we got. So we're going to go 16, and then we'll go cosine of that times 0.64, and that's 0.615. So yeah, I've got a bust on this one, so let's see what we can do about that. So that's 0.615 meters. And then I've got 16, and then sine times 0.64, and that's 0.176 meters, okay. Like so. And so that's going to probably get me some different answers. Let's see what happens here. All right. So we're doing okay here so far with what we're doing. So that changes these dimensions. This is 0.615 meters. And this other one is 0.176 meters. Like so. Okay. All right, so I'm going to change the page here and get those dimensions in there now, okay? So we good? So we'll come right here, and I'll just put those dimensions at a right angle in here, like so. So 0.176 and 0.615. All right, so now once I've got that, what I'm going to want to do is take a moment about A as I described there. So what I have now is I have RAY, RAX, and then RC, which is at 51 degrees. Like so, okay. All right, so now what I would want to do would be to go sum of moments and go a moment about A and set that equal to 0. All right, so that's going to have 3 terms. So why don't you just take a couple minutes and get those 3 terms written in there, if you would. Okay, so see if you can get those 3 terms included in there. So you're going to have 1 couple and then 2 forces. Got questions, let me know. 71, 80 copies.
No. So, no.
Oh, okay.
Actually,
Okay. Right. Yeah.
Do you have a full sheet copy of it by chance?
Yeah.
Yeah, me too.
Okay.
Just the first page.
Just the first one. Well, let's see.
If not, it's okay, I have just the one kind of scratched in there.
I don't know if I have one for everybody, but what I could do, I could just copy actually to the people next time, so.
Thank you.
You have it for next time.
I didn't do it.
You good?
Yeah.
Anybody else? If I could just copy the 271s and re-staple them on here for next time, that's no big deal. Let's just get these off. Everybody good? So you're gonna have 3 terms. Okay? I'll probably pause the recording for those of you online. You can just get them written down, then pause the recording, and then just after you've got an equation, start it up again. So to work through this, what we're going to want to do is we got 138. Now that's just a clockwise moment. That's a couple. So that will just be added in. There's no moment arm on that. So as I mentioned, that already has the moment arm on it. So that's negative 138 Newton meters. It's negative because it's clockwise. So that goes in just like that. Okay, now the RC is angled. Okay, so you have to do the trigonometry on that. So what we're going to do with that is break it into two components like that. The reason we're doing that is so we can combine the y and x components of the force with the y and x moment arms to get moments. So that's how you handle the moments. You do the trig on the forces to break them into components, then you multiply them by their appropriate moment arms. So what I would do with that first, let's say is I might go sine 51. That'll get me the opposite side, which will be the vertical side from the 51-degree angle. I've got RC, which I don't know yet. And then the moment arm on that I calculated earlier is 0.615. Okay. So that'll go in like that. Now, if I look at that, what that's going to do is come around like that. That's counterclockwise, so that'll get a plus. Okay, so that's my thinking on that. So, got any questions on that? Okay. No? And so if we're good with that, we can then do the other one. Now the other one will be the adjacent side, so that'll get me a cosine 51. And then I need the moment arm for that. So that's going to be cosine 51 RC. And then the moment arm for that will be 0.4 and 0.176 more. So I'm going to add those two things together and get 0.576 meters. Okay. Now when I look at that, that also will curl around counterclockwise, so that'll get a plus also. So those are the terms that I would apply to that. That's the moment equation. It's got three different terms on it. So do we have questions on that? Okay. So what I'm going to have then, I'm going to bring that 138 to the other side of the equation. And what's left behind then is 51. I'll take a sine of that times 0.615. And that'll be 0.478 times RC. And then I'll go 51 cosine of that times 0.576. And that'll be 0.362 RC. Okay, so I'm going to have that 138 Newton meters. And that's going to be the sum of these two. So it'll be 0.478 plus 0.362. So that'll be 0.84 times whatever RC is. So I can find RC. So I'll just take the 138 divided by 0.84, and that'll get me 164. Is that sounding about right?
Yes.
Okay. Okay. So that's the approach on that. Now, as I mentioned, I like doing the trigonometry on those angled parts of the bracket first. That way I just get everything lined out and I'm just plugging stuff into that framework for the equation. I don't like trying to do both at once because I'll make more errors that way. So that's why I'm doing the trigonometry on that bracket first. So I have everything just laid out there and ready to go. So we got any questions on that? Okay. Now to finish the thing off, you want to use force equations. Okay. Because you've got the cable now, it's 164 newtons. So to complete the problem, we just want to go with force equations next. And the way you do those is just sum of Fx equals 0 and sum of Fy equals 0. That's all there is to it, okay? The force equations are simpler. I've got an x unknown and a y unknown, so I can just do force equations to solve this, the rest of this thing out. I prefer to use those because they're easier. So I've got Rax, whoops, and that'll be to the right, so that's a positive. And then I'm going to have plus cosine 51, right? Times what I just found, which is 164 newtons. So I can solve for Rax. And see, that's going to come out to be negative when I get that, because the Rax will, will stay on one side of the equation. The cosine 51 times 164 will go to the other side of the equation. And so that'll be a negative answer. And I'm getting a negative 96.6 for that. I assumed it to the right, so what that means is it actually acts to the left. The negative answer means my assumption was incorrect. So that actually goes that way. What's that? So my... I did? Oh, okay. Thank you. So 164.
My thing I do all the time is like put numbers back.
Yeah, I think I switched them. All right, so let's see. Yeah, 103, 104, so 103?
Yes.
Thank you. There we go. So we good with that? Okay. And then you do a similar thing for the y direction. Okay. And I think we're going to get to a similar thing with the signs, because I got Ray up, and then plus sine 51 times 164. Okay. And that'll get me Ray. That'll be 127 thereabouts, and that'll be a negative. So that'll be down.
Hold on.
Yeah.
Is that 576? What is it?
What's that? Oh, on the end?
Yeah.
Yeah, the end is, it's the sum of these two. It's 0.4 plus the 0.176, so that's why that's 0.576. It's the sum of the two. So, questions on that? And as I say, I had a little bust on those answers I had originally, and they're in, I think the ones in the packet are incorrect. I don't know, maybe I might have fixed that on the new packet. I think I did on the fall 2019B. They're correct? Okay, that's what I thought. So some of you might have incorrect answers for that problem. Okay. And it would also be on the ones I handed out, I think, too, because, yeah, okay, so those are correct on that one. Okay.
It's all right, we can put that aside. Got a little.
Well, that actually, I mean, it's the right problem. It just has little dots with the wrong answers. We got the right answers. I'll send a message out with these two, so we should be good. Okay, all right. So that's the technique, and that's kind of equilibrium using trig. Okay, and I want you to know how to do that. Okay, we're kind of combining all these things we've been working on. All right. All right. Now this next one is quite similar. Okay, you've got a roller at A, a pin joint at C. Okay. So you need a free body diagram. You always want to start with one of those. Okay, so when you do this, you're going to come up with a net force right here in the middle, right? So you're going to want to find that force, whatever that happens to be, and then you're going to want a moment arm on there. Okay. And then you're going to have the reaction here at A, which is normal to the ramp. And then one thing we want to get used to on these things that have ramps on them is the force is not equal to the ramp angle. It's equal to 90 minus the ramp angle. Okay? So the angle in here ought to be 90 minus 29. Okay? And I don't know if is that a complementary angle or some, there's a word for that. I'm not sure what it is, but 90 minus whatever the ramp angle will get you the force angle, because the force is normal to the ramp. That's what's going on there, okay? So we good with that? We got any questions on that bit? Okay. And this is very similar to the one we just did. Instead of a couple, it's got a force. And you just want to go through and do, what's your strategy going to be on this one? Your free body.
What about C, right?
Yeah, right. You got these two unknowns at C, because that's a pin joint. So you're going to have RCY, RCX. I'm going to take a moment about C, being honest, that's a pin joint. And then you should be able, when you do that, you should be able to find RA. Okay. Now, once I've done that one moment, I want to come back and do the simpler equations next. So I go sum of fx and sum of fy and set those equal to 0. Sum of fx will get me RCX, and sum of fy will get me RCY. That's the sequence on that. Okay.
And then 90 minus 29, that gives me a little angle around that A, right?
It's the angle for the reaction at A, yeah,
Okay.
because it's normal to the ramp.
Yeah.
So that's why we're taking 90 minus the ramp angle, because the reactive force is normal to the ramp. Okay. So we got any questions on that? Doing all right? Okay.
Kind of treat that ramp just like a, like the opposite of cable.
Yeah, in a way. I guess ramps push, cables usually pull. It's the same kind of idea. A little bit more work to get the angle than you would with a cable, though. You know, but
Yeah.
it's the same idea. Yeah, they're one-dimensional angled forces quite often. Okay. So you get that free body diagram. There's the answers. So 453 for A. Once you've got that, you get RCX and RCY. Okay. All right. Now this one, this is probably the trickiest of the bunch. You do need a free body diagram for that. So again, I'm going to look at that and I'm going to generate my initial free body diagram for this. And what I'm going to have when I do that is I'm going to have that pin joint. So I'm going to have RAY, RAX, and then I'm going to have this force right here like that. And that will be RC. Okay. And I'm going to have that angle in there that is based on 90 minus 57. So I think that'll be 33 degrees in there, right? So that's the starting free body diagram. So that's 90 minus 57. Now, you notice there's two angled arms on this one, so the way I would approach this is I would break each arm into X and Y components. I'm going to want to do that. So I'll get an X and a Y, and then I'll break the other one into an X and a Y. Okay. Now, I want to get X and Y dimensions to wherever those forces are applied. So I'll put those red dots where the forces are applied. So I want to use the X and Y dimensions from A to B to get where the 280 newtons comes in. And then I'm going to have to do a little bit of math here to get from A to C. I'm going to have to add and subtract those different pieces together to get the total. What I'm going to want to do to get that final set of dimensions is come up with this, okay, like that. That's really what I want to end up with, to get from A to C. And that will involve just a little bit of arithmetic with those trigonometric components of the angled parts of the bracket. So do we got any questions on that? Okay. So there's the trig that I ran on that. So you got the dimensions from A to that point B, I guess we call it there at the corner of the bracket. But as I mentioned, you also then want to come up with this bit right here. Okay. And so that little right angle set of dimensions that I just sketched in there, that's based on taking the two angled sets of dimensions. Okay. So this here will be 0.639 minus 0.460. This one here will be 0.386 plus 0.285.
Why do I need the, I get the one, the left side, the vertical one, that's like my overall moment arm, but what about the little one? Why am I using the little?
Okay, I'm doing both of those dimensions because what I'm going to have to do with that RC is I'm going to have to turn it into components. I'm going to get a Y and an X for that. So the X component will go with the sum of the 0.285 and the 0.386. Okay, and then the Y dimension will go with that short little horizontal part of the Y, of the L-shaped dimension. Yeah. So to me, this is all just about using X and Y components on both forces and moment arms and then combining them. Okay. So we doing all right on that one? And you know, this is kind of the engineering kind of thing you do. You take these complicated things and just break them into pieces and approach them in that way. So we got any questions on these three that are due Wednesday? I don't know as we've got much more time to do much else, so.